builds, so does he. And I'll tell you what, brick followed block, followed brick, followed block, followed brick, followed block. The world says, it's not possible. The builder pushes on. He strikes the keys with all his heart. Here's to you, builder. Here's to ease.
Hey everyone, welcome to the first Ethereum Economic Zone community call. My name is Arman from EEZ, and I'm a coordinator of the EEZ. So I'm going to present this call. So I would like to invite first Friederike and then Jordi, Baylina, and our Zisk team as well. We have Edu, and we have Philippe, and we have Jesus. Let me introduce all of them here. So yeah, we all managed this call. Basically, what we are doing right now, 2 months ago, we announced a framework to solve Ethereum fragmentation. Today, we are going deep on why this framework makes sense. In 45 minutes, you will hear from Friederike on the fragmentation and the economics of EEZ, Jordi and Eduardo and Jesus, and also Philippe on the tech side, and they will present technical details about EEZ, and then we will answer your questions. Before we start, I just want to highlight latest news from the EEZ. We were at Prague last week, and we had a very nice fires chat with the participation of Vitalik and Jordi. Also, Jordi technical presentation record is live. Please find if you haven't watched yet. I highly recommend it. So yeah, let's start with Friederike first. Friederike, you are co-initiator of EEZ, and you have mentioned that Ethereum has a fragmentation problem, not scaling problem. Let's start there. Walk us through the problem. Why synchronous composability is the answer?
Yeah, absolutely. So I would slightly modify this. So Ethereum doesn't have a scaling problem anymore. We very much used to have a scaling problem. So a few years ago, the average transaction cost in excess of $10 on Ethereum mainnet. And in response to that, we actually got rollups on top of Ethereum, to which we offboarded a lot of the compute that previously happened on L1, driving down prices again. So we used to have a scalability problem. Now we don't really have a scalability problem anymore, but this led to a new problem, namely that Ethereum and these various rollups, they don't talk with each other in the same way that things on Ethereum can talk to each other natively. Okay, so the Ethereum economic zone is a way of fixing that fragmentation that ensued after we offloaded a lot of the compute onto various L2s.
Thank you for the detailed answer. Yeah, I mean, what do you think? What does one coherent Ethereum actually look like for you after resolving the fragmentation and the many problems with the EEZ? How do you see this coherent Ethereum?
In many ways, it looks exactly like the Ethereum we had before we got L2s, right? So the beauty of Ethereum beforehand was that things would just compose with each other. So kind of one person could build a stables protocol, another person could build an oracle, the third person could build a lending market, and the fourth person could build a prediction market. And somehow kind of like all of these could plug into each other seamlessly without actually having to ask for permission and without having to have this kind of pre-planned in some way. Kind of it's kind of this is also why we chose the Lego blocks for the video, right? So kind of this is how Ethereum used to work and what largely broke when we introduced L2. So kind of we used to have one zone with Legos, and kind of like anyone could kind of build on top of other people's Legos. And then we had different buckets, and kind of they all had Legos in themselves, and they kind of all had kind of like Lego landscapes that kind of worked in and of themselves. But building with different pieces in different Lego zones was impossible. And this has very much changed with the advances of real-time proving. So now we can actually prove the state of another chain to any other chain, more or less in real time, at least block time. So that chain can use that state as an input for its computation. Because any one network has a complete understanding of its own state, but understanding the other network state is always kind of where the trouble comes in. And until recently, proving the state of another network was slow. So you could compose, but you couldn't do it synchronously. And kind of this is the synchronous composability is where the magic comes back. And if you have that feeling again that you have different protocols on that can now very well sit on different parts of the EEZ in different networks, but that can still plug into each other as seamlessly as we used to before we actually got L2s.
So the vision is coherence, I would say. So now I would like to invite to show how actually works. I would like to invite to Jordi and Edu, and Jesus and Philippe also can easily contribute to the technical scope of the EEZ. So yeah, I hand over to my hands to Edu. Please show your presentation.
Thank you. Yeah, I'm going to share my screen. Give me a second. Okay. I think you can see it now, right? Okay. So yeah, very excited to be here today, giving an update on the current technical status with the help of Jordi and Jesus. So yeah, today we are going to cover several topics. So the idea is to give a kind of an introduction about our current status, how we end up here. Then Jesus is going to go deep into the smart contract parts, and then Jordi is going to cover the multi-proving system, and finally I'm going to give a kind of a glimpse of the roadmap that we have in mind for this technology to go to production. So yeah, our journey to the present, I'm going to try to be quite quick on this part, but just summarizing what has happened so far. So mainly we present EEZ at the ECC. We rush a lot to have something to present to the community. The idea was mainly to explain what we want to build, how we want to build it, and but also try to make a showcase about what we can do with this technology. So for that, we did the first version of the smart contract. For that, we use the research specification that Jordi did. It's a table-based implementation, and this has been explained in other talks by Jordi. For this, we try to cover as much as complex cases, just to be 100% sure that the spec at the time was capable enough to cover all the complex situations like reverts or nested call or reentrant calls. We create the repository, the organization, EEZ Association. We added 2 repositories to this one, the Sync Rollup protocol, that is mainly the smart contracts, and the Sync Rollup composer, that is mainly the implementation of this first specification. Yeah, we did a proof of concept of all this technology. We create this EEZ.dev site using Res and the book trace called many. We proved that everything works, and yeah, it was quite impressive, even for our team to be able to do that so fast. But yeah, obviously it was not a final thing. It was kind of just a proof of concept. So after ECC, when we got back to home, we started to design how we can build this for a production environment, and that is the thing that we are doing currently. So the core of everything are the smart contracts. That is why we are putting all our focus on make a final version of this, production ready and strong enough to cover all the things that we want to cover with this protocol. We did a big refactor and polish several things like naming and other stuff. Jesus is going to give you a quick intro to smart contracts. We changed this table implementation to a nested flattened approach, yes, to try to have a better, a big improvement on gas costs of this. And also we added this MN multi-proving mode that is making the protocol more flexible. So today, our expectation is to merge this new version of the smart contract, what we call it the first draft, a draft that we expect the community to give us feedback and with the idea of having something ready to be updated in 1 month or so. So with that being ready is when we can start to build the other components for production. And also in parallel, we are working on this Rollup 0, Rollup 1, mainly base rollups that allow us to prove all the functionality, to have something strong that is able to prove all the functionalities and production ready. So yeah, now we are working on all these things in parallel and try to move as fast as we can to make this happen. So now Jesus is going to jump into the smart contracts. So Jesus, your turn.
Hi everyone. Hi everyone. I fixed this slide, but it seems that it's not yet fixed, but it's okay. I will, as you see, there is an arrow, a pink arrow that is a little bit blurry, but I will explain anyway. Hi, I will do a smart contract overview as Edu presented. And well, the idea is explaining a little bit. This contract will be like kind of the center of what EEZ will settle or what EEZ allows, right? It will be, we will have a smart contract as an entry point, and I'll explain more or less the properties. One, the idea is that everyone can register a rollup. As you can see, well, maybe it's a little bit small, but in the right side we have the green boxes that are rollups. Later on, we'll see it better and bigger, but right now it's just a global overview to see what I'm going to explain. And then we'll have, so each chain can define his own rollup with his own rules, and maybe you can create a new rollup or add an existing one, like it doesn't matter, as long as you can register it here and you can kind of link the settlement or settle in this contract, you're able to join this common effort, or the chain is able to join this, or at least is how we define it for now. Then each rollup can define his own proof systems, which this is completely open and agnostic. So each network can choose to maybe to be verified by SP1 or OpenVM, Zisk, a multisig or a consensus. Like they can choose whatever proving system we call it they want, which we abstract it and we say, okay, it's whatever contract that you want, that basically you put it a input hash, so you put a parameters and you put a proof, and it must return true or false. So the idea again is this completely permissionless and it's neutral, and we provided was this framework in order to make a solution, right? Again, this contract also will try to settle all the chains together. What I mean is like all the chains together that interacts in the same set of transactions. So if there are two rollups that are interacting between them, or two chains, and we want to prove all the interactions for sure that they happen, basically they need to settle together, right? It cannot happen that one settles and the other not, and then we could have like a double spending or something like that. So if they interact together, they must settle together, which makes sense. And finally, this contract will manage the interactions between L1. So we'll see later how we kind of make a trick, or how we kind of make a contract prepared to be able to interact with L2. And from the user perspective, it will be the same as just using a smart contract that it's natively on L1, but it actually will execute a L2 logic and return the whatever it's returning. So Edu, if we can go to the next slide. Okay, I'll go now step by step of the points I said. As you see, anyone can register a rollup, and when you register a rollup, basically you say, okay, this is my rollup. There will be a rollup contract that can have it's open, how they can manage, can be a multisig or an owner or whatever. And basically you will approve some proof systems, as I say, like this abstracted thing that, for example, let's say you have a Zisk and a multisig, right? And then your rollup will settle on EEZ, but it can only be settled if you provide a zero knowledge proof that everything is correct and a signature to double check that everything is correct. That will be, for example, one setup. Next slide. Okay. As I said before, the proof system is completely open for the rollup to choose. You can pick one of n. You can do a conditions like I want only OpenVM. I want OpenVM and a multisig. I want one of zero knowledge proof, one prover that must be zero knowledge and one prover that must be a signature, for example. All this logic is abstracted to the chains or to the users, and it's time you define a prover. You can define the B key, which for those that they are not used to zero knowledge systems or ZKVMs, basically this will be the configuration or the program that you are executing for that proving system. And this is very nice because then you can easily verify multiple rollups in the same proof. So, for example, if we have 5 rollups that are settling with Zisk and OpenVM, we could have just 2 proofs for the 5 rollups. So this allows us to, or allows the system itself to scale very well and to share cost between all the rollups, which is very nice. Next slide. Okay. Here is where I explain the atomic settlement, and the slide is a little bit small, sorry, but I hope at least I can explain how it works. So a caller will be a prover, for example, or a batcher, or the entity that already has all the batches or all the transactions of the chains and the proofs. Will call EEZ with a function that's called post and verify batches. And then this will say, okay, I have this call data or these blobs, whatever, and now I will check its rollup contract, so the rollup A and rollup B, if this proof that the user or the batcher is providing me is good enough for them, right? So imagine that I'm using a proof for the I don't see almost well for the prover A, for the prover B, and a multisig, right? And then maybe it will check and say on rollup A, okay, the rollup A accepts the verifier A and the multisig, and the rollup B only accepts the zero knowledge the proof system A and the proof system B. Sorry. So yeah, sorry, the schema is a little bit small, but the point is like, basically, each rollup has been defined which prover systems accept. Here, the EEZ contract will check that we provide all the proofs necessary for each rollup, and if that's true, we will verify all the proofs of all the proof systems, and if everything returns true, we accomplish the settlement, right? We will be able to settle multiple rollups in the same transaction, which is very nice because this allows, of course, they can both not only verify their own transactions, but verify the interactions between rollups. And for instance, we allow this synchronous composability. Thank you. So, okay. So to manage, now let's see what happens when we verify this proof. And this is very linked to how we manage the synchronous composability between L1 and any chain that is not L1. So when we verify a proof, we update the state of each chain that was verified. Like before, we update the rollup 1 and the rollup 2. And we append or we store in the contract something that we call an execution entry. An execution entry, it will be safe. Basically, the L1 interactions, and now I explain what we are doing. So we are not ever doing any optimistic like stuff in the sense that saying, okay, I will interact L1 to L2, right? And we wanted to do it synchronous. So when the user interacts with the contract, with any L2 contract, we want already to have been proven this execution, so we can already know the result of this execution. So what that means is when the system verifies a proof or when the system does this verification, it advances itself in time, or it kind of predicts the transactions in L1 that will happen, and it will have, let's say, a response for that. So, for example, to do an easy example, imagine that we want to do a bridge, or we want to just send Ether from user A to user B, but user B is on another rollup, right? So then, and that will mean that we will add an execution entry that basically we will put in the proxy entry hash, which is how we define these interactions. We define, okay, we expect that the user A send 1 Ether to this address in L2. Later, we see how we manage these cross-chain proxies or cross-chain transactions. But basically, we expect a L1 transaction to happen. If it does happen, it will match the execution entry. It will update the state. As we see, there is an entry that's called state deltas. We'll update the state of the rollup 1, and we'll return the value if it's the case, which in this case, no, because it was a plain Ether transfer, right? But this is very powerful because you can extend this on whatever you want. So you can make the same interaction, but now instead of a user, you interact with another smart contract and it returns your value. And then there you go, right? You accomplish asynchronous composability. The user just interacts with a smart contract and it gets a return value in the same transaction. So from the user perspective, he didn't go out from L1 and it already interacts with L2, right? And you can even go ahead and make nested calls. So you can even call L2 and then L2 can call L1 again. And then we encode these L2 to L1 calls inside of this execution entry. So this can get more, more complicated, but also more powerful, right? Once you have this structure and you're able to prove this structure with zero knowledge, basically you allow a lot of possibilities. You allow the users to interact with any chain, and it's true that from the prover perspective and from the building perspective, you have to do more work. But from the UX perspective of the user of the apps, it's amazing because they only see one chain and they just have to interact the same as always, and they have an instant result, right? So let's see an example. So this will be, yes, this will be the first example because the other one is a little bit more complicated, which is a user that interacts what we call cross-chain proxies. So what we do to make an experience frictionless basically is to create cross-chain proxies, which means that its address of a rollup, or let's say rollup A, its address of a rollup A anyone can permissionally create a proxy in Ethereum, right? For example, I want to interact with user B, so then I will need to create a proxy for the user B in Ethereum, right? And once I create this proxy, that is forever, and I can interact with it, and that will be the same as sending Ether to the user B in rollup A. And this can be extended to the contracts as well. If there is an Uniswap on rollup A, can create a proxy of the Uniswap, and if I interact with this one, with this contract, it's the same as interact the Uniswap on rollup A. So as we see before, this interaction, the user just calls the proxy as it will call any smart contract with any call data, and the proxy just forwards this call, to the EEZ contract. And then EEZ contract will do what I explained before that we see. It will kind of hash, right, the interaction that we did. So we'll say, okay, it's calling rollup A to this address with this call data. It will hash and we'll say, do I have an execution entry for this call? Yes. So if it does have it, it will update the state of rollup A or rollup A, sorry, and return any value or the other complicated stuff that I explained, or the nested calls if they are. But in this case, it's a simple case, so it's not. Then it will return the data, and it will return the data to the user, which in this case, it is doing nothing because it's a normal example, but you can just return values in the same transaction, which is pretty cool. So next example. So the example is similar to the other one, but now we have a nested call, right? Now we have this weird case, which weird or normal, let's say, which we call a rollup, and when I'm calling a smart contract on layer 2, this smart contract calls me to L1 again. I'm sorry that the schema is a little bit small. Maybe I should put this schema somewhere. But the first part is the same one, right? The same thing. But there is one point where it changes, that when we go to the EEZ contract, instead of returning right away, we then execute all the L2 to L1 calls that in this case, I said foo, it's calling a contract C with a foo call data. And then I make it even more difficult because this contract, so this L2 is calling to L1, so this rollup A is calling to L1, and then this L1 is calling again to L2. So as you see, you can go as further as you want. Doesn't matter. Once you build the system, is the same thing, kind of proving one or more. Once you prove the whole nested thing, it's the same to do it more than once. Of course, it's not easy to go there, but so as I was saying, you call this contract C from L2, and this contract C calls again. Maybe you don't see it, but it calls again rollup B, so another contract with another address. And this another contract with another address on another rollup can return a value, and then the contract C will return, and then finally EEZ will return a value to the user or return a data to the user, right? So maybe it's a little bit complex example, but I want to show up that you can do like multiple cross-chain interactions, like L1 to L2, and then L2 goes to L1, and L1 goes to another L2. You can do whatever you want. Like this schema, it's pretty flexible and allows all of those interactions. And next slide. And yeah, and again, this again the first schema that we saw. I hope that now it seems a little bit more familiar, or you understand it a little bit better. And I hope it's a little bit useful to and understand a little bit better how EEZ is working from the smart contract perspective. And thank you so much.
Okay, so thank you so much, Jesus. Now, Jordi, it's your turn.
Yeah, hello. I want to explain a little bit how the proving system is. Well, first, we already mentioned, but I think it's important to mention that the system is not it's not. So it can be as many proving systems as you want. So anybody is able to define a proving system, okay? And the rollups will decide which proving systems they accept to modify the state, that they are following the rules, okay? So it's not limited to one single proving system, and it's not married with a specific proving system. Actually, these proving systems could be ZK proving systems, could be T proving systems, could be signature proving systems, can be one, many. And this is important because it will allow rollups to define these 2 out of 3 proving systems. Maybe it needs to be correctly Zisk and SP1 and maybe one signature one. So each rollup will be able to define which one. Maybe this is rollup contract that Jesus mentioned. I think this is an important thing. Okay, so how will all these proving systems, how they connect all together, because we have like we have an execution. Let's see what we have to prove. Okay, so way to see what we have to prove is when we have calls, we have random calls between rollups, or even between L1 rollup and L2 rollups. Actually, we can divide the way of dividing with what's the minimal chunk. I mean, what's the minimal part that's happening? Well, a minimum part is an execution that happens. It's a small execution that there is no rollup change. For example, in a normal transaction in rollup A that's calling rollup B and then returning, I mean, normal return, it will be 3 chunks of those. Okay, so one transaction 1 that will start. So we'll start a transaction 1 and we'll do a call. Then another chunk that's going to happen in B, that B will do the execution in B, and then the context will go back to rollup A, and there will finish with this will return, and it will finish the execution. So we have like 3 chunks, 3 execution chunks. Okay, so if you have 10 transactions and they are calling on each other, we can have like thousands of these chunks. Okay, in this chunk, this is defined in a single rollup. It's a state transition function. We call it we call action-driven state transition function, but it's very much. I mean, it's like a more generic thing. State transition function generally refers to a transaction. An action-driven state transition function, it can be it refers to an action. An action can be, for example, a call. So it's not a transaction; it's a call that you receive there. Okay, and this update your state. Okay, so in this call, this will be three pieces of there. Okay, so all this table. So when we have like many transactions, we have this table. Okay, and this is very much what we have to prove. I mean, each prover system will have to prove one of these chunks. Okay? But actually, from the L1 perspective, if we can you go to the next slide? If we go to the next slide, so if we go, so what we see from just an L1, so in this case, if we are executing, I mean, it is a call, it's just a roll up. So in the case of the layer 1, we see something, it's like another table, but it's a derivative of this. Okay, so in the layer 1, they say, okay, if you do, so you can execute a transaction, the inaction is null because it's just a transaction, and the result is null because this is just executing one transaction. But saying, okay, if you're executing this transaction, updating these states, the state of the rollup A and rollup B, according to this is going to be correct. Okay, and this table, this is when you are creating a batch, this is very much what you are building in L1. Actually, you are building all these requirements from what you see from the L1 perspective, and you are hashing it together. So what you need to prove is that this table is correct. Okay, inside the proving system, you should have deterministically a way to go from this first table to the second table. This is for a single transaction that updates 2 rollups, because a transaction that is touching 2 rollups. But if there is, if you have, for example, 10 transactions that touches 3 rollups between them, this could be just a single entry that goes from here to here. Okay. The problem is that when you have transactions that also interacts with L1, you need some extra information. Okay, so you can go to the next slide. Okay, so in this case, for example, it's from an L1 to a rollup A. Okay, so here we would have actually here I put here 3, but here we will have like 5 different chunks. Okay, the first and the last chunk, because they are happening in L1, they are not in the table, but actually imagine that they are there. Okay, and here we would have, this is a nested call. So you call here, okay, and the rollup 1 is calling L1 again, and then you go back and forth. Okay, so how this will be translated? If you go to the next state, actually this would be translated in what you need from L1. Okay, and what you need from L1 is something that's a little bit more difficult. It's not just some modification of a state transition functions. Okay, but it's a mistake here, but it's okay. It will have, it's like, okay, in order to execute this transaction in L1, is like here you need to also do some inner calls on L1, and you would expect something L2 calls in there. So this structure is a little bit more complex because it's everything. So all this structure is everything you need in order to execute those transactions in a consistent way between L1s and L2s. Okay, and all these, the L1 to L2 calls, the expected L1 to L2 calls, and the execution entries, this is what will be hashed from the L1 smart contract. Okay, so this is here. You will have only like interactions with L1, but all to the L2 they will be. I mean, you will not see there. I mean, they will be kind of hidden. Okay, but they will be in the initial call. In this call, this will be extensive, but you don't need to hash that in L1. This can be a hash, and this is just shared with all the rollups. Okay. And the idea is that this translation from the first table to the second table, all the proving systems will have to verify that. Okay, and each proving system will verify the parts of this table that affects to themselves, and only the proof will be accepted if all the proving systems, if all the proof of all the proving systems are correct. Okay, and in the hash you will also add which rollups needs to be verified in each proving system. Okay, so this is what gives the full system is consistent. All this happens in a single transaction in the smart contract. So smart contract is very easy. At the end, it's just one transaction where you build all these call, you pass the proofs of all the proving systems that you have, and you check that those proofs are correct. And very much that's it. You execute all these transactions by very much updating the states of the rollups and by executing the things in L1 that requires for all these transactions to happen, and of course checking that the consistency is correct. Okay, but important parts. Many proving systems. So the system is multi-proving system. You can use multi-proving systems, and they share the same structure. I mean the same, but at the end is a table that hashes it. All of them, there are some pieces that are common to them that all of them need to verify, and the system is correct if all the proving systems are correct. If there is, of course, one malicious proving system, this would. So all the rollups are safe except for the rollups that, of course, they are accepting this malicious proof system. Okay, but if the rollup that there is at least the rollup that his proving system, it's a 2 out of 3, push 2 out of 3 are correct, then that rollup will not be able to be modified. It will not be able to be updated unless they are following this action-driven state transition function. There is more details. I would love to explain longer in some other sessions or in person, but this is a little bit the big idea for the multi-proving system. I don't know if Edu or Armagan, you want to continue?
Yeah, I can continue, but Jordi, I don't know if you want to mention about these 3 points that you had in your slides about the smart contract representation, proof system selection. It's a summary, I guess, that you did.
Yeah, I think that Jesus already mentioned that each rollup is represented by a contract. Important is that, I mean, a rollup can be absolutely decentralized, stateless. It's a rollup with no owner, nothing. I mean, this is perfectly possible. Or it can be a fully centralized rollup where you can update the state, you can do whatever you want, and you have very high sovereign. Okay, and the system is widely. When anybody should be able to define a rollup. The idea is that all these smart contracts, they shouldn't be updatable. This is the idea. So the system should be fully decentralized. It should be, fully trustless system. It's just a smart contract running on Ethereum. This is the idea that we are building, and it's absolutely permissionless. So anyway, anybody should be able to define their own, the rollup, and everybody should be able to define their proving system. And it's just a matter of accepting each other. Okay, and this is very much the I think I already mentioned everything in there.
Okay, this is mainly a summary. Yeah. Okay, moving forward, I'm going to talk quickly about the roadmap. Probably today we have go too deep into details about the smart contract, but mainly that is because it's our current stage. We are just finalizing the smart contract right now because we expect to start to audit as soon as possible. Our intention is to have a final version by mid-July after audits and after all of the reviews. That is why we want to go deep on this part, mainly because we expect to have some community feedback on regards of this smart contract, because at the end of the day, it's the core of our system. That is why it's important for us to have something flexible enough to cover all the cases and something that is strong for the future. Apart from that, we are currently working on several fronts in parallel. We are working on the composer and the multi-sig prover. So at the end of the day, we need to implement this smart contract functionality to provide this data to the smart contract. That's mainly what the composer is doing. And also, we are starting to add in multi-proof system and verifiers. So yeah, our intention is to have the first rollup live by mid-June with the idea of having maybe not all the functionality, but at least the most important functionality, L2, L1 calls, L1 to L2 to L1 calls, having the proving system. So it's obviously a reduced version of what we want to expect to have, but at least something that allows us to mature this technology and to make it production ready. And after that, by the end of the summer, we expect to have the rollup one, a basic rollup that fulfill all the vision that we expect and allow us to show to the community how any rollup can use this atomic composability to interact with the network. So yeah, I mean, we expect to start to give more updates about our current status, and also probably we need to create some specific content to explain technical details, because as you have detected, it has quite complexity and it's not easy to maybe understand at the beginning. But yeah, we are having this intention to explain as easy as possible to anyone, and and allow anyone to provide feedback to us. So yeah. This is more or less the technical update. So thank you.
Thank you, Eduardo. It was pretty nice and detailed presentation, and thank you all the Jordi and Jesus. Tech is solid, real-time proof atomic execution. So I want to talk about the economic effects of EEZ, and I would like to invite Friederike here to talk about more. So I am inviting Friederike again and removing the Jordi and Jesus. Hello again. So let's talk about a little bit of the economic aspect of EEZ. We saw a few stage 2 solutions was introduced more than 2 years ago. They are all great technically. They are brilliant teams, but we see a relatively low adoption. How will EEZ be different from the other solutions, and what does actually mean for the economically?
That's a super fair question. So if you look at stage 2 rollups, what makes them stage 2 is the security guarantees, right? Kind of like they have the same security guarantees as Ethereum. At the same time, they have significant drawbacks. So kind of you rely exclusively on layer 1 validators. You have one block every 12 seconds with Ethereum, so you can't have faster block times. It kind of, as always, kind of you have the chicken and egg problem, right? Kind of like you kind of have a you have an ecosystem that kind of you need to build up, while you actually have pretty large proving costs, right? Kind of like if you want to get into every block, then kind of this is a significant overhead, and then kind of you need to make sure there's enough activity to actually make that economically viable. What the Ethereum economic zone does differently is kind of, I mean, the Venn diagram of kind of like what base rollups and what rollups within the EEZ do or can do is basically a smaller circle in a larger circle. So kind of base rollups can very easily become parts of the EEZ, but other rollups can become part of the EEZ too. And what the EEZ natively offers is a way to synchronously compose. And in principle, this is also possible for base rollups. It's just something that was never really built end to end because real-time proving is a pretty pretty new thing. So kind of I would say kind of you had the security guarantees that that Ethereum gives you kind of for base rollups. You did not have the network effects that kind of we see in the Ethereum economic zone, right? So kind of the idea behind the Ethereum economic zone is that you can touch applications across different parts of the Ethereum economic zone within the same transaction, meaning you don't actually have to rebuild everything from scratch on your network. You don't have to endlessly replicate systems that are already there on other networks. Same for liquidity, right? So kind of if you look at a lot of what L2s do today, it's they're basically swimming against the current, right? So kind of like they have to make sure they have liquidity for the relevant token pairs. They need to make sure they have DEX protocols deployed in money markets and all the other DeFi primitives people come to expect. They need to make sure they have the right stables deployments. They need to make sure they have on and off ramps, SEX integrations, oracles, identities, and so on. And so kind of what we actually ended up with in the larger Ethereum ecosystem is Ethereum plus a couple of mini Ethereums on top of Ethereum, where kind of basically everything that Ethereum has is replicated in some shape or another, and that doesn't this doesn't engender network effects, right? Kind of like you want something where you can bring something new to the table. You can plug into an existing network, and you can add kind of a specific use case or a specific user group or kind of a proving mechanism, or you can add privacy or fast blocks or whatever you want. You can have a consortium chain that kind of that where you control the validators. You can have a lot of different chains that can bring different things to the table without having to replicate what's already there. So kind of the tech behind base rollups is really good. I would say kind of a lot of the thinking kind of has informed the architecture of the Ethereum economic zone. But also kind of, I mean, we see L1 scaling now for the first time, right? So kind of like if you actually look at the history of L1, kind of the scaling efforts we've seen so far have been largely L2 based, but kind of now we can actually scale L1 with increasing the gas limits and kind of doing also ZK proving on L1. So kind of to the extent that possibly bandwidth actually becomes the main constraint in building blocks. And I think in this reality in which we're heading, kind of the L2 and adjacent ecosystems that we'll need are ecosystems that complement L2, not ecosystems that just replicate the same value proposition that kind of Ethereum already fulfills. So kind of stage 2 L2s, they they were quite restricted in kind of the user experience that they offered to dApp developers building on top of them. And the Ethereum Economic Zone basically now allows all kinds of rollups, and technically you don't even have to be a rollup to kind of join the Ethereum Economic Zone. And I think that's the beauty of it. So it's maximally permissive in terms of who can partake. It's not opinionated. It's open source software. It belongs to everyone. It should belong to everyone. And I think that's going to be what will ensure that this is the architecture that we will see for Ethereum in the future.
Thanks for the super comprehensive answer for this question. Yeah, we have a lots of topics to talk, and I believe it was a detailed stream for our first community call. Let's say it's the Genesis community call. For more talk, for more details, we will be at the DAppCon in mid-June at the Berlin. I invite everyone who interested in synchronous composability in terms of a technical wise and economical wise. We are planning a workshop, and I want everyone here. So yeah, that's wrap. Thanks for everyone joined our call. Hope everyone like this detailed first community call. I just want to say thank you, and see you in the next call.
Bye, guys.